in this lesson, we're going to mix together the different types of distributions, discrete ones that is, and our challenge is going to be identifying which type it is, and then remembering to use the correct formula. So here's the types. We have a uniform. And when we do a uniform distribution, we're looking at an experiment that's being done just once, and everything has an equal chance of occurring. So for instance, you roll a dice, and you look at the side. You flip a coin. You buy a lottery ticket. Okay? They all have an equal chance of happening, and you're just doing one thing. Option 2 is binomial, so we're going to do things repeatedly, but the probability of success in each trial is what you're measuring. Okay? And that probability never changes. It's independent of one another. I roll the dice, but I'm doing it 5 times. I flip the coin, but I'm doing it 3 times. And then, of course, the third one, hypergeometric, we're doing repeatedly, but probability changes each time. So I have a deck of cards, I deal with the first card, and I keep it out. Okay? The probability is changing with the next card now because one of the cards missing already. So those are our 3 types: uniform, binomial, hypergeometric. So in this first one here, I'm just going to do some examples today. Let's take a look at, try and identify the type of distribution we'll be looking at. So 6 marbles are taken from a bag containing 10 white marbles and 12 black marbles. What is the probability that 3 white marbles are chosen? I don't want to do any math, I just want to talk about the type. So I have a select group of items, and I'm taking out 6. So I'm doing it more than once. So it's definitely not uniform. So my choices are binomial or hypergeometric. Does my probability stay the same, or does it change? Well, as soon as I start taking the first marble out, I have less marbles to choose from. That makes this hypergeometric. It's dependent trials, and they are repeated. I'm doing more than one marble. Okay, let's try B. A single die is rolled 5 times. Oh, did it more than once. What's the probability that 6 will appear on the up face in exactly 3 of the rolls? So if I do it more than once, it's binomial or hypergeometric. Does the probability stay the same, or does it change? Well, what I got on the first time has no effect on the next dice. So this is the binomial one. These are independent and repeated. And then the third one, 20 tickets number 1 to 20 are placed in the hat. A ticket, a single one, is randomly selected. What's the probability that ticket numbered 7 will be selected? Well, that's uniform. Okay, we have a single trial, and every probability is equal. I have an equal chance of picking any one of those tickets. Okay, so those are our 3 types. We're going to try to identify before we try and do the math. So let's try the first example, or second example, I guess. In a computer chip factory, 35 out of every 1,000 chips produced are defective. A batch of 20 chips is chosen at random. So we're doing something repeatedly. This is a independent event. Just because my first chip is defective doesn't mean my second chip will be defective. That's a random sample of 20 chips. We don't know how they interact with each other. So this is a independent, repeated situation, which makes it binomial. Yeah, let's see what the questions are asking us. What is the probability that exactly 3 chips are defective? So we're looking for x is 3. Our formula, as you might recall, is n choose x, p to the x, q to the n minus x. That's probability. So in our case, there's 20 chips chosen at random. I want to find 3 chips that are defective. My probability of defective, well, 35 out of every 1,000. P is 35 out of every 1,000 then, or in other words, 0.035. It's a very small chance of finding a defective chip. So 0.035, and I want to find 3 of them. Q will be 1 minus 0.035, or in other words, 0.9965. Say 965. And I want that to happen 17 times. So 3 successes, 17 failures. Into our calculator we go, and you should get 0.0267. Okay, part B. What is the probability that at least, at most, 1 chip is effective? So no more than 1. In other words, less than or equal to 1, which we know means we have cases. Probability of 0 or the probability of 1. We're going to do these in 2 separate stages. So what do we got? We have 20, choose 0, 1. Nothing to be defective. P is 0.035 to the 0. Q is 0.965 to the 20. Plus 20, choose 1. 0.035 to the 1. So 1 failure, or 1 success, 19 failures. Add those two things together and hopefully you get 0.8461. And look at part C here. How many defective chips would you expect in the batch? So an expected value is just an average. And we know our expected value for binomial is just n times p. How many trials? Oh, we picked out 20. And the probability of finding one at any one batch? 0.035. Math-wise, we get 0.7. So we expect less than 1 defective chip out of every 20, which seems reasonable. You only have 35 out of every 1,000, right? Not very often you get a defective chip. So there's an example of a binomial one. Let's take a look at the next one. A bin of fruit contains 4 apples and 8 oranges. 5 pieces of fruit are randomly chosen from the bin. So we're picking repeated. But in this case, we have a starting group. We only have 12 things in that bin to begin with. As soon as I start taking one out, I know the probability is going to change. So this is dependent probabilities, which means this is hypergeometric. This is a choosing situation. So similar kinds of questions. Probably exactly 3 apples are chosen. 3 apples. Okay, how many apples do I have to choose from? I have 4. I need 3. And that implies that I need to choose 2 oranges, because remember we have 5 altogether. Out of the 12 things, and we want 5 of them. A standard combination question. Punch that into our calculators, and we should get 0.1414. I'll try B. What's the probability that all of the pieces are oranges? So we're picking 5 things, so all that means X is 5. All right, oranges, how do we get those? There's 8 of them. Apples, we want none of them, and we want 5 things altogether. All right, into our calculator we go for that one, and we should get 0.0707. So basically half as likely as the previous one. How many apples should you expect to get? So our expected value, again, it's proportions. How many trials are we doing? We're doing 5. The proportion of things that are apples, well, there were 4 apples of the 12 pieces of fruit. So 4 out of 12. That's my likelihood of getting an apple. So we get 20 over 12, or in other words, 1.67. I should expect 1 or 2 apples. Look, another one. We've got 2 left for you. You roll a single die and observe the up face. Single die, up face. We're doing one thing. That's telling me this is uniform. If I did it more than once, I'd have binomial die independent events. We're doing it once. If you roll a 1 or a 6, you win $5. If you roll a 2, 3, 4, or 5, you lose 2. Is this a fair game? Well, we know based on past experience, fair means expected value is 0. Equal chance of winning or losing. So let's calculate that. Okay, I have a 1/6 chance of rolling a 1, and if I do, I get $5. If I roll a 2, however, I'm going to lose some money. I'm going to lose 2. A 3, I lose 2. A 4, I lose 2. A 5, I lose 2. A 6, I win $5. Okay, so each of the cases, or if you will, it's 1/6 times 5 minus 2 minus 2 minus 2 minus 2 plus 5. In other words, 1/6 times 2, which is 2/6. So odds are on average, I'm going to come away with money. So is this a fair game? No. Not a fair game, since EX is not 0. you actually have a better chance of winning money in this game than you do losing it. You come on the positive side. Okay, last one. I need you guys to try some. A school lottery has 5,000 tickets for sale. There's one grand prize and 5 second prizes of $100. What is the expected value of the lottery, and explain what it means? So again, this is expectations, and it's a uniform question. You're buying a ticket. So the likelihood of winning first prize is 1 out of 5,000. The value of that is, hey, you win $2,000. Or there's 5 second prizes, so 5 out of $5,000, and you win $100. And really, the rest of the prizes, the other, we've got 6 so far, so there's 4,994 of the 5,000. You win $0. We just don't usually show this, right? Because that's what it means, but times 0 and you've got nothing left. So what is our expected value? Well, it's 0.5. So what does that mean? On average, each ticket is worth 50 cents. That's the average value of each ticket. That's what you have to give out per ticket. Part B, how can the school use the expected value to help determine the ticket price? Well, it depends. Do they want to make money? Do they want to break even? Do they want to lose money? Right, to break even, charge the 50 cents. To make money, charge more than that. Depends on how much you want to charge, right? Then you have the whole buying and how much can you charge without have people still buy things. Okay, that's the end of this unit, actually. We're going to spend time mixing them together today. The homework is a handout. It's on the website. The answers are there. You can try them out. The math is not going to change today. No new math. It's just trying to mix them and identify which type you have. Remember how to do each type.